and I'm going to focus about a very underrated technology in building cooling, which is evaporative cooling technologies. And I would like to show how innovative evaporative cooling technologies can serve the purpose of decarbonizing the buildings. My agenda for today is that I'm going to discuss why decarbonization matters. Well, I am going to talk about an approach which is called as an adaptive comfort approach, some basics about evaporative cooling, water as a refrigeration, and then how we can manage this evaporative cooling with all our air conditioning systems. So that's what we call as hybrid cooling systems. So I'm going to discuss that. Before I start the evaporative cooling, let me just reiterate what ma'am was telling. We know today buildings account for approximately 30% of global CO2 emission. Energy consumption in a building, HVAC is the largest energy guzzler. It's the largest energy consumers within most of the buildings. The cooling demand is increasing, as was again highlighted by ma'am. And then we have our own net zero energy and net zero carbon goals as per COP this thing. And we have to all be we know that we have to be net zero carbon by 2070. So those are all the net zero goals which we have already laid on. So what is HVAC decarbonization? So we will focus both operational and embodied carbon associated with HVAC systems. This can be achieved through key strategies. How to lower the energy demand of HVAC systems. How can we shift from high global warming potential refrigerants? And then how can we maximize the use of renewable powered low energy technologies like heat pumps and even air conditioning systems. So that's the roadmap for HVAC decarbonization. I like to focus upon this, what we call as an adaptive comfort approach. So gone are the days when we were talking about thermal comfort of maintaining 22 degrees centigrade temperatures in our spaces. Even our room air conditioners now start at 24 degrees centigrade. So what's this approach? So for HVAC engineers, there is a standard, which is HC 55 standard, which gives an adaptive comfort model. What that model means is that when you have a mean prevailing outdoor air temperatures, higher mean prevailing outdoor air temperatures like in India, wherein your temperatures can go up to as high as 48 degrees centigrade, a person can even feel comfortable at 30 degrees centigrade, 32 degrees centigrade with right amount of air velocity, right amount of humidity and everything. So this adaptive comfort approach works very well, especially in the naturally ventilated building. It has a higher tolerance to temperature variation. And the biggest advantage is that we can use a lot of low energy cooling strategies in this kind of buildings. Like Roshni ma'am was showing this Indira Paryavar Bhavan. I'd like to highlight there that in that building, we have used a technology which is called as a chilled beam technology. So in a chilled beam technology, you can design the the air cooling system or the chiller system at a very elevated temperature, higher temperatures. So these are all low energy cooling technology strategies. So I'm not covering those technologies today, but I want to focus on something which is very unique and which we all know very well, which is evaporative cooling. Now, evaporative cooling is not a new technology. It has been used for ages. So we have been using evaporative cooling since long period. And in fact, when you talk about cities which were hot and dry, like Delhi, Jaipur and all, we all used to have something which was called as a desert cooler or a simple cooler in our house. So that worked on the principle of evaporative cooling. It's the best low energy cooling technology which can be used very well in today's buildings, especially when we are talking about naturally ventilated buildings. What are the advantages? It's a water-based cooling, so there is no harmful chemical, there is no harmful refrigerant. It's a 100% fresh air system. It's an enhanced ventilation system. So you can have, there are no issues about indoor air quality, because in an air conditioned space, you have a lot of recirculation of air. There's always an indoor air quality is a challenge. So because of this 100% fresh air system, the ventilation, the indoor air quality is taken care of. The energy savings is huge. you don't have any compressor in this machine. So you can actually save almost 60 to 80% energy when compared to your DX cooling systems or your chill water based systems. And then you have performance zones. Obviously, these technologies work very well in hot and dry, but we can also club it, or we can also marry it with a refrigeration based cooling system to make sure that we can also design these kind of system in hot and humid climates like Mumbai and Chennai. So, coming to the basics of evaporative cooling, as I mentioned earlier, direct evaporative cooling systems is something which we have been using. This is basically, there is a pad on which the water is sprayed. There is a fan. Because of the evaporation of water, the air is cooled and some amount of moisture is added to the water. That is called as a direct evaporative cooling system. Then we have something which is called as indirect evaporative cooling system, which I'll explain in my subsequent slides. And then we can club these two technologies, direct as well as indirect, to make something which is called as a two-stage evaporative cooling system. And then finally, we can also have these hybrid evaporative cooling with a mechanical cooling system. So what we call as hybrid air conditioning. Plus, we can also marry this technology with a lot of solar systems, solar thermal systems, solar PV systems, to make 100% net zero energy building or net zero energy system by using renewable energies. So those are also possible. So let me explain you what is direct cooling. So direct evaporative cooling is, as I explained earlier, water is being sprayed over the pad. The air, hot air comes in contact with water. The water evaporates. It takes the heat from air. So the air temperature goes down and some amount of moisture is added to the water. So there is no harmful refrigerant used. There is no artificial refrigerant used. It's the world's most natural clean refrigerant, water, which is R718. Now, this is something which is new. This is called as an indirect evaporative cooling system, because what happens is, when I mentioned in a direct evaporative cooling system, what happens is you tend to add some moisture or the water vapor into the air. So when you add water vapor into the air, your when it comes to your building, you always have a problem of what we call as humidity control. So there we have a unique now system design, or a heat exchanger design, wherein the heat exchanger will only reduce the temperature. It doesn't actually add moisture to the air stream. So these are called as indirect evaporative cooling systems. Again, they work on water only. So if you see on this right side, we have this this heat exchanger here. It has two air streams. This is what we call as the primary airstream, and then there is something which is called as the secondary airstream. So typically, let's say I want 100 units of air here. I would design this fan for 135 units, and the 35 units of air is used as the secondary air. Now, this secondary air is coming in contact with water, and it is evaporatively cooled. So only the secondary air, only the 35% of the total air quantity is evaporatively cooled, and the majority of the air which is going from left to right is only sensibly. Sensibly means only the temperature is going down. There is no moisture being added. So this is what we call as a indirect evaporative cooling system, wherein only the temperature is reduced, no moisture is added. So that's where you can actually address that problem of humidity control in the conditioned space by using an indirect evaporative cooling system. Now, why water? Water, because it has no ozone depletion potential. It has no global warming potential. It is safe. It is abundantly available, and it is eco-friendly, totally eco-friendly. So that is why any evaporative cooling system is always 100%. It's a net zero carbon system. Just to give you some GWB and ODP values of other refrigerants. So you see R410 has a GWP of 2088, which is very high, and R134A, which we use in our package units and windows and splits, is almost 1430. Now, as I was mentioning earlier, that we can always club this technology with a refrigeration based or a compressor based technology. So this is what I wanted to highlight. So we can design a hybrid air conditioning system. Anybody can design a hybrid air conditioning system. So when it's hot and dry outside, so when it's summer, as we call it in our northern part of India, then you run this system only on air cooling mode. You run it on two-stage evaporative cooling mode. When you have high humidity, then you switch down the second stage when where we are adding the moisture, and you trigger or you start your mechanical cooling. So that's called as hybrid air conditioning mode. And then when you have winters, you simply ventilate the space. You don't run, neither you run the water nor you run the refrigerants. So that's how you can have a simple free cooling, as we call it, mode in this kind of a system. So hybrid cooling saves a lot of energy. It can be used year around in even hot and humid climate. We optimize our mechanical coil usage. So we use the refrigeration system or the mechanical cooling system only when the humidity is high, and this has a a very significant. It can offer a very significant savings for us. So that's where I would like to end my presentation. We all want to reduce our electric energy consumption, especially on the HVAC side. We want to reduce our peak electrical demand. We want to near zero refrigerant emissions, and we want to improve our indoor air quality, because at the end of the day, buildings are built for human beings, and we have to be cognizant of the fact that air quality will always impact your productivity and health of the organization. Thank you. Thank you for my time.
Thank you, Mr. Rahul, for your valuable inputs. Okay.